It's my pleasure to welcome Dr. Subho Dasgupta sir from IISc for this session as a speaker, as a resource person. I would just brief sir about this particular FTP. So this is a AICT ATL sponsored FTP titled Novel Materials for Next Generation Applications. And the participants for this particular FTP are from various colleges from all over India, as well as PG scholars, research scholars from various backgrounds such as mechanical engineering, material science, chemistry, and physics also. And even some of the participants are from electronics background too. So I would like to introduce Professor Subho Dasgupta's by reading out his brief profile. Sir, Professor Subho Dasgupta was the recipient of Doctor's Gold Medal from IIT Kharagpur in 2005. He received PhD in Material Science from TU Darmstadt, Germany in 2009. Next, he worked as a group leader at Karlsruhe Institute of Technology, that is KIT, from 2012 to 2016. He has also served as a visiting scientist at Lawrence Livermore National Laboratory. Presently, he is an assistant professor at Indian Institute of Science, Bangalore. He has 45 journal publications and 14 patents submitted or accepted to his credit. His primary research interest includes printed electronics, oxide electronics, 2D materials, nanoporous solids, electrolytic field effect, printed supercapacitors, and gas sensors. So this is a brief biodata of today's speaker. So I leave the virtual stage to Dr. Subho Dasgupta. Yes, sir, you can start your session.
Yeah, okay. So hello, good morning, everyone. I hope you can hear me well, right? So first I would like to thank Dr. Pradeep Kumar for his introduction, and also to Dr. Panish, who actually invited me to this FTP program. So my topic of today's talk would be like the session name. So I will talk about some emerging electronic materials and devices, and in particular I will focus on a certain specific variety which is called flexible and printed electronics. That is my primary research area. So in the second section, when I will focus into this flexible and printed electronics, I will show you some glimpse of our own research as well. Okay.
Sorry to interrupt, sir. Please switch on your video, sir.
But it cannot go both, right? Okay, start my video. Let me see. Okay. Okay.
Yes, sir. We can see you, sir.
Yeah. Oh. Okay.
It's fine, sir. You can continue, sir.
As Dr. Pradeep said, that today the audience is a mixed audience. So you are from different discipline of science.
There's been a disturbance, sir. Your voice is not clear.
You can't hear me?
Your voice is not clear, sir. There's been a disturbance.
Dr. Pradeep, you can't hear me?
Just try with switching off your video, sir. Now, sir.
Dr. Pradeep, can you hear me?
Yes, sir. Now it's crystal clear.
So So now can you? Yeah, so I think the bandwidth is not sufficient that I can also run the video.
Yes, sir. That is
but
a problem. Yeah, now you can share the screen and you can continue, sir.
Yes, but without the video, you can hear me well, right?
Yes, sir. I can hear you well.
Okay. Okay, so let's start again. So as Dr. Pradeep said that today's audience is a mixed audience and you are from different science and engineering discipline. So to start with, I wanted to introduce a new concept to you, which I call, tailoring versus tuning. So what is this concept? The concept is that in one end of it, like the left column of the screen, you see that there are structural materials, okay? And on the other side, I have put functional materials which will make certain type of devices, which we will discuss today. So this will be based on the electronic properties of materials, okay? And these functional in devices will primarily be the devices which are interfacial in nature. So we will slowly see that thing. So, but first about this, differentiation between structural and functional materials. What I wanted to say is that when we talk about a structural materials, we need certain type of mechanical performance. What happens that we work with the so-called this famous triangle, structure, property, and performance and processing, correlation. Okay, what we do there, we want to work with the composition of the material and also microstructure. That is what material scientists, mechanical engineers, they do. Okay, so we introduce some defects. It can be point, line, and volume defect, and we want to control the mechanical performance of the material so that certain structural application can be addressed. Okay, but here all these properties during the synthesis of the material is decided, and then they are frozen in within the material. Okay. On the other hand, if we talk about the functional material or devices, what we will see that the main criteria is that these are electronic materials, and the properties would be tunable by application of an external stimulus. Okay, and that is what will give us a device. Okay, and these can be controllable. Properties can be electronic, magnetic, photonic, mechanical, chemical, and so on. I will give you some example how we do it. But I think it's understandable. In one case, structural materials, where the properties are frozen in, they are controlled by tailoring the composition and microstructure. And on the other hand, functional material, of course, we do the tailoring. We try to come up with a certain composition and microstructure for certain purpose. But the device is basically based on use of an external stimulus, which controls the property between two states, if not more. Okay. So again, this tailoring of these material properties, mechanical properties for structural materials, they are irreversible. We can call that for tuning, it is reversible and dynamic. That is what I meant. That electronic properties are such that by application of a small stimulus, which can be electric field, I will show you a larger, table where you can see that what can be the stimulus and what kind of property we can control. Okay. On the other hand, but the structural properties are, as I said, it's typically frozen in. I can give you one example. Let's say we use when we have some teeth problem. Okay, so there are some cavity or some defect. Then we use certain filling material. So this filling material is soft initially, and when the dentist does some local curing by a laser or something, then it hardens. Okay, and now if you break a part of it, what needs to be done, unfortunately, is that you will be given a local anesthesia, and then they will drill it and try to get the whole material out. Okay, because once this material is hardened, it cannot be made soft and malleable again. So this is the problem of structural materials, that we define its performance by certain processing and treatment, but typically that kind of either it can be a soft and malleable, or it can be hard and brittle. Material scientists would say that I can do annealing to go between one place to other, but that's not really a soft stimulus. Okay. On the other hand, for functional properties, electronic materials and properties, a very soft stimulus can change the property, and that is how we get the devices. And as I said, most of these electronic devices, they are interfacial in nature. So the interface is the important thing here. Okay. Now, as I said, I will show you a list of stimulus on the left side and the physical properties of materials which can be controlled. So let's assume if the stimulus is electric field and you want to control electronic transport, then the device name is transistor. What we do in transistor, we control the electronic transport through a semiconductor which is placed between two metal electrodes, which are called source and drain electrode, and we try to control the electronic transport through this semiconductor material by application of a field on a third electrode, which is called gate electrode. Okay, so this is a device transistor. Now, if we try to use the same electric field and try to control the mechanical property, or let's say length change, okay, so that could be actuator. If it is length change can also give us some sort of sensors, okay, and it can be also dielectrophoresis kind of things, okay. So this we see that the same external stimulus, which is electric field, which actually comes under a general category of electric potential, and we can change electronic transport or mechanical behavior of a material. Let's say then I give you an example of magnetic property modulation, which is called Magnetoelectrics. It's a spintronics is a growing field. Okay, if we try to control elastic property of a material, it's called Electrochemical fluid, which is extensively used in industry. On the other hand, if it is not electric field but some sort of electrochemistry, electrochemical reaction, again we can have magnetic property modulation, which is called magnetoionics. We can have optical property modulation, which is called electrochromism, and there are also electrochemical sensors. Similarly, if it is the stimulus is magnetic field, we can have electronic transport modulation, which is called magnetoresistance. There are different type of magnetoresistance, as we know, depending on what we are controlling. It's a spin-dependent scattering, or it's a spin-dependent tunneling that gives us GMR or TMR effect. Okay, if we try to control elastic property by a magnetic field, it's called Magnetological Fluid or ferrofluid. I think some of you may also have heard about it. So these are also extensively used in industry for heat transfer or as magnetic valve. If it is electromagnetic or photonic, the stimulus, it can be electronic transport, which is IR, photo, UV sensors. It can be optical transparency, which gives us so to say photochromism or photochromic glasses. Probably that there are some even spectacles which are like if you go under the sun and then it turns dark. Okay, it becomes like a sunglass. So that is based on this property, the photochromic effect. Again, the nature of stimulus is chemical. It can be a large set of electronic transport control and large set of sensors. So this is just a very beginner level picture. There can be more stimulus or more physical properties that can be tuned. But what I wanted to say until now, that there are structural material where we want to have that material for mechanical property. Certain mechanical property it has, but in those cases typically we tailor make the material. That's what the metallurgist or material scientists do, try to make a certain material with a certain property. Okay, maybe good toughness, maybe good creep property or fatigue property, whatever it is. You will see in general it is controlling the composition or microstructure of the material, but then this material is irreversible. It's the same in its lifetime. On the other hand, the functional property and such devices, of course, requires tailoring as well. But typically, the very low, at a very general level, we can say that it is always we use a stimulus, external stimulus, and control a certain physical property of these materials, and that gives us certain device. This is what I have listed. So I will actually talk about some of these I just quickly touch upon, not the very common ones. I think what is actuator, right? What is magnetoresistance, this TMR head we use in our hard disk drive. These are known, right? So I will go for some little bit less known ones, less known examples, and then what I have highlighted in green, this will be the second part of my talk, which will be basically flexible and printed electronics, which I will show that it's a new emerging field where we do make certain type of device, transistors and circuits, electronic circuits for certain new class of applications which are beyond the silicon technology. Okay. So to start with, I will just very briefly talk about electrophoresis. So what is electrophoresis? Electrophoresis is basically, as I said, this is again the stimulus is the electric field, okay, and then the electric surface charge and zeta potential. And what is zeta potential? It's also a coulombic charge at a particle surface, and that we can control. And if it is positive charge, we call it cataphoresis. If it is a negative charge, we call it anaphoresis. But the idea is the same, that we want to move the particle based on the type of charge it has, okay, on its surface. And its use is that this earlier level of this older Amazon display, Amazon tab display. So these are not the new ones, which are these different technology, but older time when this tab was just this, it used to be called Kindle. So this tab was just for reading books. Okay, initially Amazon started like only selling online books, right? So that time it was an electrophoretic display. And what was the idea? The idea was that you will have a TiO2, which is white. TiO2 is a large bandgap semiconductor, but when it is nanoparticle, due to scattering, it all looks white due to the light scattering. So they use TiO2 for the white pixel and some polymeric nanoparticle, which is some kind of a pigment particle, which is for the black pixel. And depending on they are within two layer, which are conducting layer. Conducting means that probably we know a very well-known transparent conductor is ITO, tin doped indium oxide. So they are this TiO2 or this polymeric pigment particle. They are in some sort of a kind of bulbs or spheres. They are placed inside, and those are placed inside in between two transparent conductor layer, okay, which can be ITO, okay. And then when we apply certain charge from outside, like it is shown in the picture, negative or positive charge, then we can either bring this black pigment particle at the surface or the TiO2 particle at the surface, and that's how we did have pixel which will have its color black or white. And this was a black and white display. This Kindle, what I am talking about, the earlier, I think they are still available. They're very nice because they have a very nice backlight, which is not strenuous for the eyes, and the refresh time, which is 120 millisecond in this technology, that's also sufficient, and we can really use it like a replacement of a book. Okay, and that is the technology, which is electrophoresis. Next is dielectrophoresis. It's same. Is this electric field control movement of particles or small nano size species based on their dielectric property. Okay, so other one was electric and it is dielectric property. So it can be positive dielectrophoresis when this dielectric constant of the particle is greater than the dielectric constant of the fluid, or negative dielectrophoresis when the dielectric constant of the particle is less than the dielectric constant of the fluid. And what is the idea? We have certain particles inside a fluid medium, and then using their dielectric property we can guide them or move them in a certain direction. And this can be used for again wide range of application. For example, medical diagnostics and separation and sorting of species, chromatography and microfluidics and so on. So I give you one example here, which is work long back in 2003, but that was a good benchmark work. And in the domain of this dielectrophoresis, what they have done, this work group, they had single one carbon nanotubes. And if you want to make a device, you know that you need the semiconducting ones. If you want to make a transistor, you don't need the metallic ones. But there are a lot of strategies how to sort them. But this was a strategy to sort them in situ on the substrate. So you know that these carbon nanotubes, probably that based on their how this it comes from a graphene sheet, let's say, and then you roll it and then it's stitched. And at the time of stitching, how it's stitched, depending on that, we get something called chirality. Okay, and this chirality determines that it would be metallic or semiconducting. Okay, fortunately, what happens, the dielectric constant obviously for the metallic and semiconducting ones will not be the same. And using that, it is shown that it is possible that you can place those only the semiconducting ones at the at this electrode gap. So what I am showing here on the left side of the image, so this is a substrate made full of electrodes where the sharp tips, probably you can see those sharp tips protruding. So let's assume these electrodes are those two electrodes of a transistor, source and drain. Okay, and then there are sharp tips, and then we want to have a nano wire bridging this sharp tip, and this has to be a semiconducting one in order to make a device. So using this concept of dielectrophoresis, this is possible. So this is what I show you now. This is a SEM image and TEM image combined. No, this is a SEM image fully. Okay, so what you can see that again you can see those electrodes and sharp tips, and using this dielectrophoresis we want to have this gap is breached by one nanowire, and that is possible because once that one nanowire bridges it, then there is an electric field or the current is passing through this nanowire. So as long as there is no nanowire bridging it, there is a certain electric field, and using a certain AC frequency we can create a condition where only the semiconducting ones, due to their certain dielectric constant, they will come and bridge the gap. And in this way it's possible to have more than 1 million CNTs per centimeter square of the substrate, making those devices. So you can see that in these gaps there would be one CNT bridging the gap. And if, what has been shown in the right side is just a zoomed picture, and here you can even see the CNT. Okay, the carbon nanotube which has bridged this two sharp electrode tip. So this is a use of dielectrophoresis. Next, I think I will also spend 1 or 2 slides to explain electrochromism. We said that there is another concept where you can use electric potential in the form of electrochemistry. Okay, if you remember that large table, that there was first was electric field, and then it was electrochemistry. And using electrochemistry, you can also control optical properties. In this case, the optical transmittance. Okay, so some layer would be transparent or not. That you can determine. How you can determine using electrochemistry? So there will be an electrolyte, and there will be certain ions, and they will have a redox reaction, a Faraday reaction with this specific material, okay, and actually it's a surface chemistry, but this new material will have certain different, band gap, and will also have a certain different color, okay, or certain different, transmittance. So what is the use of this? This can be used as smart houses, like it is shown in the first picture. On the other hand, the Dreamliner, Boeing 787, their windows are now these electrochromic windows. Earlier we have the shutter. Okay, so we in the in older older it's just two state. Either you open the shutter or you close the shutter. With this kind of electrochromic window, they give you four buttons, which you can see probably. I mean, let me try to get the pointer. So this is where the buttons are. Okay, so a person who is sitting he can operate it to have in not just a black or transparent, but four different states like it is shown here. So depending on the applied voltage, okay, we can really control the amount of light which will come in. Okay, so we can really control the transparency. Okay, so this is the advantage. It is not two state, binary, either shutter down or shutter up. Here now we can have different shades, okay, from fully transparent to very dark. Again, here the switching time is low. It's only in the order of some milliseconds. The reason being that this is a surface chemistry. This is not a bulk chemistry. So therefore, this can be really used as smart houses, or as I said, that this can be used also. These are in use in now new Boeing 787 air carrier. Okay. And how it works, I already told you that this is an electrochemical reaction at the surface. So in this case, for example, if the material is tungsten oxide, which is a famous material for electrochromism, then you can have also there are a lot of organic material, a wide variety of organic material, which also gives a wide range of color. But one very commonly used material is this tungsten oxide, which can react with some metal ion. Preferably the electrolyte is lithium based, so lithium goes in, and then you have a lithiated tungsten oxide, which is dark blue. The pure tungsten oxide is transparent. Okay, so this is also the cross section of the layer, and it goes for even 10 to the power 5 to 10 to the power 6 cycles. So the large number of cycles, that means if a flyer is using it 2-3 times during his flight, it's okay, because these air carriers are for long distance. Okay, so in one day, if it is used for a few times, it doesn't matter. If the lifetime is 10 to the power 5 to 6 10 to the power 6 cycles, then it will go on for years. So it is ideal for this kind of application. So here again, a periodic table and different materials: tungsten oxide, molybdenum oxide, niobium oxide, vanadium oxide, and so on. And you can see that their oxidized state is transparent or light yellow, and the reduced state is blue or blue-black. So you can really change the transparency by a large extent, and you can also have intermediate states, as I have shown you. Okay. So this is another advantage. You can really control the amount of light which you want to pass in. Then next is this magnetological fluid or ferrofluid. I think some of you may be very much familiar, or maybe really working in this domain, because it's a popular work field in India. So I will not get into much of a discussion. So this is again. So this is a ferrofluid. It's small magnetic particles. They are preferably superparamagnetic. Okay, and then they are dispersed in a liquid medium, and typically the particle loading is extremely high. And then if you apply a magnetic field, you can change the rheological properties. You can change the viscosity of the material by a huge extent. So from complete liquid, you can get to a certain shape and not really solid, but it can work again have large can have large range of application in heat transfer, and also in microfluidics, and as I said, magnetic valves, magnetic traps, and so on. So, for example, they are gamma Fe2O3, magnetite or magnetite. They are common material which one can use. Okay, and I think it's understandable that when you apply the magnetic field, you can allow, that the whole material, this fluid becomes kind of rigid. The rheological property or the viscosity changes by a large extent, and then you can use it, as I mentioned, for a lot of application in space research, biomedical, and so on. Okay, now one more example, which is like exactly what I have told you in the beginning, that it could have been very nice if we could have a structural material where we can change its structural properties also by a small stimulus, not by annealing. Okay, heating at high temperature and cooling down. So that's not really a stimulus, but electric field or magnetic field is a stimulus. We can do it back and forth. And this has been shown also. So here the idea was that the young modulus or a strength of a certain materials has been tuned. What you can see on the right hand side, the blue curve shows a large extent of ductility, and the red curve shows that it is kind of brittle. And how can you get it? You can get it through by electrochemical reversible oxidation of a nanoporous gold. So what it is a nanoporous gold sponge, like it is shown in the SEM image. Okay, and how it is made? This is typically made by a process called dealloying. Dealloying is that it's a process of selective electrochemical leaching of the less noble material from a binary, or even it can be ternary alloy. So typically they are alloys which are completely solid soluble. Let's assume gold silver alloy. Okay, so we take a gold silver alloy, and then if we take it into a certain electrolytic medium and apply a certain electric potential, then we can, it can be alloy. It doesn't need to be gold silver, it can be brass. Okay, so we can always etch out the less noble material first. This is the idea, that gold is more noble, silver is less noble. So then I can apply a potential such that it only will etch out or eat out the silver. And then there is a self-assembly process goes on. When you do this electrochemical leaching, and what you get at the end is a nanoporous material, like it is shown. So now, if we take this nanoporous gold sponge and then put it in a different electrolyte, okay, and what we can do, even gold can be electrochemical oxidation is possible even for gold. Okay, so we can have a very thin monolayer of surface oxide. But this is already, since it's nanoporous, the surface area is so high, then even if you have 1-2 monolayer surface oxide, you can change the mechanical property by a huge extent. So that has been shown. The blue curve here is when it is pure gold sponge. The moment we have a little surface oxide electrochemically, then it is brittle. So you can go between these two phases at your will, just by applying two electrochemical potential. I put one potential, there is a surface oxidation. I put another potential, the surface oxide is gone, and in one case it's ductile, and it has it can sustain a lot of strain. In other case, it's hard and brittle. Okay, so even that mechanical property now people have shown that can be reversed by an external stimulus very nicely back and forth. Like what I gave the example initially, that it would have been so nice that it gets partly broken, I could really make it soft again and take it out. But that's not possible. what the doctor needs to do is a local anesthesia and drill it, and you get a pain for next 3 days. But if there would be a material like that we can easily go between soft and hard phase, that can serve, not only this is just one example, but that can be also many other nice examples where we can use it. Okay, now if we move to this control of magnetic properties, I said that there are electric field or electrochemistry can control magnetic properties, and these are called Magnetoelectrics or Magnetoionics. Okay, so this is a part of the whole global spintronic activity. Okay, and the idea here is to control magnetism by an external stimulus, like we control electronic transport in a transistor. Okay, so what we live in today in the society is all made by those little device transistor, right, where we can control the electronic transport through a semiconductor by application of a little external field at the gate electrode. Can we do the same with a magnetic material? Apply a little electric field and control magnetism. Here, unfortunately, God has given us silicon and a lot of other semiconductors, but the magnetic semiconductors are rare and they are not so great as the let's call it electronic semiconductor. In a standard semiconductor, the electronic transport we can change by a large extent, what we call a on-off ratio in a transistor, right? So we can go from near metallic to near insulating state, right? The channel conductance in a best known transistor we can alter by 10 orders of magnitude. Okay, so that is not really possible, unfortunately, for magnetism, but people have tried. So here one example where some thin iron platinum or iron palladium film, thin means 2 to 4 nanometer. So first few examples I will show you which are with itinerant magnet. Itinerant magnet in the sense that these are 3D metallic magnets. Okay, and then I will show you some other examples as well. So this is one with this 3D metallic magnet, 2 to 4 nanometer of iron platinum, iron palladium thin film. By electrochemical electrolytic field effect, I will later explain in greater detail what I mean by electrolytic field effect. So with electrolytic field effect, people could change the coercivity here, okay, by a few percent. Okay, so it's not complete control on magnetism. Then came another work by another research group from Japan, where they wanted to control a very ultra thin layer of iron, 1 to 2 nanometer or 2 to 4 monolayer. In the right hand side you can see the magnetic hysteresis. The red curve and the blue curve are measured at two different applied voltage, so they are actually applying a large voltage and trying to create a large electric field. And then you can see that saturation magnetization is not changing, but the susceptibility is changing, the remnants is changing. Then came one work from Chiba and co-workers, where they even went down to 1 monolayer of metallic magnet, cobalt. So here it is important to note that why these are so thin, why people went for 2 monolayer, 4 monolayer, 2 nanometer, and here even 1 monolayer. Before I explain the result, here people got a little bit better success, but before I explain that, it is very important also to note that why so thin. The reason being that we know that metals have a very low screening depth. What is screening depth? It's mean field penetration depth, Debye length, or Fermi-Dirac screening length, different names through which we know this. So this is like how deep the externally applied field can penetrate from the surface of a material before it's screened by the charge carriers inside the material. Okay, so for example, for undoped silicon, the screening depth can be 300 nanometer. Okay, on the other hand, For a pure metal like copper, it can be only 0.5 angstrom. Okay, so you can see that it's a large difference. And why this large difference? Because of the carrier concentration of the said material. A metal has a very high carrier concentration, okay, a pure metal, and therefore it can screen any external field very effectively. Okay, it doesn't allow it to penetrate much deeper. It can screen within sub-monolayer of atom. And this is what the main problem is, that the good magnets are metallic magnets, right? I can control the charge carrier and I can control the material electronic property as such for a semiconductor deep into the material by, for a large thickness, okay? That's why when we talk about transistor, we don't say that the semiconductor must be 1 nanometer, okay? Because we can control the material electronically much deeper inside. On the other hand, if it is material like a metal, in this case is the 3D magnetic metals, we can only control it to 1 to monolayer, very thin. That is the problem, and that's why in this example it is even they went for 1 monolayer of cobalt. You can imagine it cannot be less than this. So for 1 monolayer of cobalt, now the success is a bit more. You can see that they could control the coercivity and also they could control the magnetization. You can see that this fourth plot here on the right hand side, for plus 10 volt they have a magnetic material, and for minus 10 volt it's nearly paramagnetic, or you can really call it on and off switching on and off switching of magnetism. But that's possible only for very thin film if it is a metallic magnet. Next comes this magnetic semiconductor. So these are called DMS, dilute magnetic semiconductor. In this case, it's a 8 nanometer diameter quantum dots of manganese germanium, and you can see the manganese is much less than germanium. And these are dilute magnetic semiconductor. There was once upon a time lot of work in this domain. Here also people could show some tuning. Okay. In this case, you can see that by application of certain electric field, you can change the magnetic hysteresis. And there are many, I think the top three, the first row, the top three picture is measured at 100 Kelvin, then 200, and then 300 Kelvin. So at least at lower temperature at 100 Kelvin, the the change is quite drastic. As you can see, it is more or less going from 0.2 Bohr magnetron per manganese ion down to 0.05. So, and at room temperature, the control is 30%. Okay, so this is field control, field effect, or electric field control of magnetization. Then at some point what we did is the other thing, what I called here magnetoionics. It was Magnetoelectrics and this is magnetoionics. What we did here, we wanted to control the magnetism by electrochemistry. So that was a new area of research which we wanted to start. Okay, so here the idea was that electrochemically you control magnetization of a magnetic material, and here the chance of success was higher in a larger volume of really a good quality magnet or a strong magnet. Okay, the reason for this is that a field effect is weak. As I told you that for a metallic magnet it cannot penetrate beyond 1 monolayer or sub-monolayer. But if it is electrochemistry, we know that electrochemistry can be of various kind, like surface chemistry, which is then the name of the device is supercapacitor. There can be also bulk chemistry, where the name of the device is battery, lithium-ion battery, sodium-ion battery. It is bulk chemistry. Okay, and if it is chemistry, it's not only change of charge state of the material, it is also the change in there would be a lot of distortion inside the material. Okay, and that is because that you are inserting a new ionic species inside the material, so the bond length, bond angles, many things will change. And if some of you have some background in magnetism, then you know that for the for the super exchange systems, we have something called the Goodenough Canonical rules, right? GK rules, and what that says that the angle, bond angle, MOM angle, is very sensitive, and it can switch you between antiferromagnetic and ferromagnetic states. Okay, so we wanted to do something similar. What we did lithium intercalation, lithium chemistry, like a lithium ion battery. Okay, but our electrode was a magnetic electrode. So we started with a gamma Fe2O3, maghemite, which is basically a magnetite with some vacancy, with some vacant metal interstitials, we get this material gamma Fe2O3 maghemite. But to some extent it's like magnetite Fe3O4, which so it's a superexchange mediated system, and it is a material which is spinel, and it has space to get new it has space for lithium to get in. And when we put such lithium ions inside, then what we can do here, it is shown on the right hand side. This is in situ measurement electrochemistry. So that top right curve is so-called charge discharge. Okay, it's a charge discharge cycle, CP mode, chronopotentiometric mode, charge discharge between two. It's like a battery testing. But in the bottom curve, which is measured in situ in a PPMS, magnetometer, you can see that very nicely the magnetic moment or magnetization is following this charge discharge. Excellent. Okay, and this is 30% change at room temperature. But important thing is it's not monolayer. It is a bulk. You have what we had is a nanoparticle. We took nanoparticle and then like a battery electrode we made. And now you know that battery electrode can be as big as we can think of. Any car batteries are really big, so you can use milligram, grams, or even larger quantity of material, and there you can control magnetization. Again, you can think of electric potential controlled or electrochemical controlled application of this in drug delivery, in microfluidics, in magnetic valves, traps, a lot of application domain. Next, what we did, I did not go too much into detail because I don't have time. There was certain reason to believe that if we go from iron ferrite to copper ferrite, we can have, and then to zinc ferrite, we can have larger and larger control over magnetization, and that's what we did in couple of years later. And there we have observed 50% change in magnetization for copper ferrite. So the red hysteresis is as prepared. After fast discharge, you can see that 50% reduction in magnetization. Fast charge, means discharge means lithium in, fast charge means lithium out, because we are using it like a half cell, and it's the magnetic electrode is like a cathode. Okay, so fast charge means lithium out. Fifth discharge, again fifth time lithium in, again it went down. Fifth charge, again it came back. So it's very reversible, like it has been shown in the last slide. You can see that a battery can easily go for thousands of cycles, few thousands of cycles, and you can get this magnetization tuning in a bulk material also for that kind of large number of cycles. Okay. To choose the right extent of lithiation or lithium intercalation, which will not destroy the crystal structure. So this is very important in this whole thing what we have done, and I want to tell you that it has to be a material which the structurally remains unchanged. For a battery, there are different types, right? One is called intercalation, and one is called conversion reaction. In a conversion reaction, you change the crystal structure from one type to other and back and forth, and it's not like that. If you go for intercalation, you can get very nice magnetic switching, and also it can go on for large number of cycles. So basically the batteries which are used in our daily life, like our mobile phone or our laptop batteries, they are all intercalation type. Okay, then we moved. This all was spinel, and these are super exchange system. Then we moved to a system where it's an intermetallic, manganese, zinc, antimony, intermetallic. Okay, and there was certain reason why we went there. But again we have done some electrochemistry. This little plot in the left hand side below is called cyclovoltammetry. Okay, so using this electrochemical method, cyclovoltammetry, typically for a battery you can, or in an electrochemical system, you can know that what is exactly going on in the system. So using that, we again determined a certain suitable electrochemical potential, and here again we could get 75 to 80% control of magnetization. This is again an in situ measurement. So you can see on the right hand plot, bottom plot, that we are doing this electrochemistry, which is this dark yellow line. Okay, so this is this discharge charge cycle, and we are measuring magnetization in situ. Okay, at the same time simultaneously, and those are given with this blue round symbols, and you can see that the magnetization is going from 25 mu per gram or ampere meter square per kg to down to 5. Okay, so it's a 80% change in magnetization even for an intermetallic system. Next, we give two more interesting examples. Okay, this was the work where the plasmon frequency of ITO, as I already mentioned, ITO is what? It's a tin doped indium oxide. It's a very famous and well-known transparent conductor. It has extensive use in everywhere: touchpad, anti-static coating, and all your mobile phones and laptop screens. Everything is ITO coated, which you can touch. Okay, so if you have a wherever you see touchscreen, until now it is primarily this transparent conductor which is used there, ITO. Okay, so for ITO we can tune the plasmon frequency, which is shown at the below at the two plots at the bottom, by application of an external electric field. So why it's the same thing? ITO is somewhere in between a semiconductor and a metal. It's called a degenerate semiconductor. Okay, it has a carrier concentration of the order of 10 to the power 21 maximum, 10 to the power 21 per centimeter cube. Okay, whereas a pure metal would have well above 10 to the power 22. But this ITO is the mean field penetration. What we were saying is sub-nanometer, sub-monolayer for metal. Here it is of the order of 1 nanometer. Okay, and if you make small nanocrystals, this is sufficient to control the charge carriers in these particles, and you can see a large change in the plasmon frequency, controllable, tunable by external field. Okay. Next, another example where photonic metamaterials, photonic metamaterials resonance frequency is controlled. Okay, so again the same thing. These photonic metamaterials are shown in the left hand side, above the left above picture. The photonic metamaterials are shown, and then there is again you can control electrochemically. Okay, so these metamaterials are made of certain shape of gold. Okay, metamaterials. So if you know, so there are certain specific shape we artificially create to get some specific range of optical properties or photonic properties. Okay, so this is shown that even if we create that, and then you can apply electrolytic field effect. Why electrolytic? Because it has a very large very large electrolytic capacitance values are very high. Okay, so you can tune or you can the surface charge density can be extremely high. Okay, and if that is the case, what is shown in the left right hand side picture, so here this is the applied voltage. Okay, this is the applied voltage, and if you can see the resonance frequency is just following that. So even for a photonic metamaterial, the resonance frequency can be controlled by a stimulus, by a electric potential, okay, or by electrochemistry or electrolytic field effect. Okay, so now I think I have reached to the midpoint of my talk, or the half of my talk is done. What I have shown you until now is that, again, if I spend 1 minute to revise the entire thing, that on one hand we have structural materials. These are materials which are designed specifically for certain set of mechanical performance parameters, but these performance parameters or the properties of these materials are typically frozen in unless you do a annealing or of that sort of intervention. Those properties do not change during their lifetime. Okay. On the other hand, you have functional properties and functional materials. Here the idea is this will be also tailored. There will be also composition and microstructural control for certain benefit. But the main idea is for all the electronic device you can think of, that you can generalize into my table, what I have shown you today. You can generalize everything into that. You can put that into that table, that I have an external stimulus. Using that, I control a certain physical property. Okay, this is generally true for everything. And what is also generally true for all these devices, if you go back and see that they're interface dominated device. So devices, all these electronic devices, whatever you see around you, okay, everything is interface, not the bulk. For structural material, the bulk is important, right? If you want to make a bridge or make a house, you need not only nice interface or nice surface, but for this functional devices, is everything interface. A bad interface, bad device. A good conformal interface is a good device. Okay, so these are typically interface dominated, all these devices. And what you can also generalize, that here there will be always an external stimulus which will control certain physical property. And I have given you some examples which are non-standard. If I talk about actuator, okay, there are plenty of examples around us. So I have not discussed those. I have just tried to give you some example of non-standard stimulus property combination, let's put it this way. Okay, so after that, now I will move to a specific domain here which I have not talked so far, which is transistor. And the reason being, so this is also an example of emerging area of research and application. It's called flexible and printed electronics, the new set of electronics or semiconductor materials and electronics which is beyond silicon. Why beyond silicon? Because silicon, we know, it's a covalent crystal, and covalent crystal has a very high bond strength and very specific directionality, and that's why silicon cannot be bended. Okay, you cannot bend silicon. Okay, so there are certain set of examples and applications possible where you need to bend the electronic material. Therefore, you need to look for alternative semiconductor material technologies. And there is also something called printed electronics. What is printed electronics? As opposed to conventional lithographically made electronics lithography and then some ultra high vacuum techniques. That's what we do for silicon technology. Very extremely high quality lithography coupled with extremely good clean room and UHV techniques for growth of films. Okay, as opposed to that, printed electronics aims to go from solutions, from inks to print electronics, different type of electronics that I will introduce you today. Okay, so this is a view graph which shows global trend in printed electronics. Many of you may not even heard this word, printed electronics. Okay, but you will be surprised that how the market is growing. Okay, and this has, in this view graph, you have displays, photovoltaics, lighting, RFIDs, and others, and the market is growing in a very rapid manner. Okay, so in 2020 it's 7.8 billion USD, and in 2025 we are expecting more than 20 billion USD for this market. And this driver for this growth is this IoT, Internet of Things. We have a lot of, more and more amount of electronics which will surround our life, and then at some point you need inexpensive way to make those electronics. Okay, they may not be as good in performance, they may not be as good as as good as silicon technology. Those microprocessors will not be that high performance, but that's not necessary. It is necessary to have a volume production and inexpensive production, and therefore we will go for printed electronics. And this OLED, for example, OLED technology, organic light emitting diode, that is now already, I will also show you some examples. They are already, it's a commercially viable through different type of printing, and there people are doing that. So if we talk about the front end of a display or front end of a high performance TV, we can already print it. We cannot print the backplane, but we can print the display. Okay, so this is another view graph where we show all sort of application on the right hand side, and on the left hand side and the right hand side. What we show that when we say printed electronics is not only transistor and circuit, it will have conductors. Okay, even printing of silver for touch screen. As I said that ITO is the transparent conductor. It can also be a transparent conductor if we simply print a silver mesh. Okay, so wherever there is silver line, that will be used for conducting the current. Wherever there will be a square gap, that will be used for transparency. So even a printed silver mesh kind of structure can also be a transparent conductor. Okay, so it can be conductors, sensors, photovoltaics, battery, electroluminescence, electrochromic displays, what I just talked about it, electrophoretic displays, what I already talked about it today, OLED lighting, OLED display, logic and memory. Everything comes under the big umbrella of printed electronics. So even light emitting diodes, photovoltaics, okay, these all can be printed and are being printed actually. So here what I wanted to say is that color versus electronics. What is color versus electronics? We know printing. We know that our newspapers are printed, our t-shirts are sometimes printed, and a lot of other things are printed, and there we print with colors. Okay, RGB or CMYK, different colors we print. In case of electronic printing, what will change? Here it is very simplification to say that the difference is only the inks, but the machines also changed. But here the main idea is that instead of printing different color, we will print different electronic gradings. What is meant by electronic gradings? I will come to that in the next slide. Okay. Now about little bit historical development. Actually, even before the invention of the transistor in 1902, Albert Hansen introduced the concept of printed electronics. Okay, so he printed some metals at that time, because as such printing is very old, as this printing was also there 3-4 century back. Okay, so the printing as such, the printing techniques are very old, and to be honest, from 3-4 century behind we started to do modern printing, but there are some proofs that even before Christ there was some proof of printing in China. Okay, some sort of replication which can be called printing. So it's a very old thing. So then in 1902 there was the printing of some metal, which can be said that the first conceptualization of printed electronics. Then, Paul Eisler, he proposed a printed circuit board and took a patent in 1936, even before the first demonstration of a transistor in 1947 in Bell Labs. Okay, and then there were certain developments. More importantly, in 1997, a fully printed transistor was shown by Jen Bao at Bell Labs. Okay. Now I introduce you to different new terminology. These are all come under the big umbrella of flexible and printed electronics. Okay, so these new terminologies are organic electronics, plastic electronics, flexible electronics, paper electronics, transfer even paper can be used. So you can print on a paper, and that is electronic circuit. Okay, and it is really true. Even we do that. Okay. On the other hand, textile electronics means you can print on your T-shirt. Okay. So now you have some colors and fancy photos you print on your T-shirt. Just think about how interesting it will be if it is something something interactive. Okay. Maybe there is a picture which is changing. Okay. They are switching from one picture to other, like a billboard, but it's on your T-shirt. Okay. So that can be possible. Okay. So these are the different examples. Transparent electronics also can be used for smart windows. Okay. So there are thoughts where when you press a switch. Okay. So that those kind of things are can be possible. Wearable electronics is for a large volume use of electronics. Let's say it can be used on every consumer product what we buy from the supermarket. Okay. And depending on these terms, there can be different active materials, there can be different substrate materials, as I said, and different fabrication methods as well. Okay. So when we talk about printing, before we go deeper into the subject, when we talk about printing, we talk about some contact printing, replication type. What we see, everything what is printed items we buy from supermarket. In supermarket, we buy a lot of stuff which comes inside a plastic bag or a some sort of a container where something is printed on it. Okay, nearly everything what we buy. Okay, and they are typically done by flexography and offset, mostly flexography. So these are contact printing and replication type, very good for volume production. There are another type of printing. So printing can be subdivided into two major parts, where it is non-contact or jetting type. Here comes inkjet, aerosol jet, electrohydrodynamic jet, and some sort of 3D printing. So this is again some pictures of some other solution processing techniques, like the first picture is for spin coating, then the second picture is for spray coating, third picture is for chemical bath deposition. On the other hand, these are some other printing techniques. So this is inkjet, this is aerosol jet, this is electrohydrodynamic jet, and this is gravure, and this is screen printing, right? So these are some pictorial representation of some printing techniques. And then I came back to why printing. I already told you why printing, because it can give you volume production of devices on variety of substrates, very inexpensive compared to silicon technology. In terms of initial investment, let's say to make a fab lab, you need $5 billion, and what I have in my lab, the initial investment is not much, and we can and circuits. I will not show much into detail because I thought today it may not be the right audience to get into much deeper into what we are doing. But that is the thing. I mean, what I wanted to say is the initial investment is very less. You don't need a clean room. You don't need lithography. You don't need UHB growth technique. It can be substrate independent. Lot of different substrate, as I said, it can be glass, it can be plastic. Plastic, what we have in supermarket, what is 99% is PT. It's a very cheap plastic. Okay, so all these water bottles or Coca-Cola bottles, they are PET. Okay, so this kind of plastic, or as I said, even paper can be used. It's a green technology in the sense technique. No ink will be wasted. Everything optimized. You run the printer. You are printing volume. I mean, even when you print color, do you waste the ink? Not so much. So it's a very high low waste technique, and the market volume can be enormous, and it can be, I mean, the main idea here that if you print, it would be ultimately volume production means roll-to-roll printing. So your substrate has to be flexible and your technology has to be flexible. And then on the other hand, you can also address certain type of application which is not possible by silicon, because silicon is not flexible. Okay, so it will create a new market in future. That is what we see. So when there was, I mean, after development of the technology, many times the new market is created after development of the technology. When the technology was not there, we didn't even know what we can do with it. When the technology is there, then you can think of new market opportunities or new application domain. Now, I said that I will show you in a few slides that what we mean by inks in case of printed electronics. Okay, so here the inks are not RGB, not red, green, and blue, not colors. Here the inks are electronic gradings. So electronic gradings means here we mainly mean 3 different type of ink that can give us all sort of electronic device. In general, in a very general platform, we can say 3 different type of ink: conducting ink, metallic, semiconducting ink, and insulating or dielectric ink. Other than that, as I said, that our substrates will be plastic PET, which can go up to 120 degrees centigrade, and cellulose paper can go only up to 100 degrees centigrade. Okay, so therefore our technology must be very low temperature. Okay, so the technology has to be very low temperature processable. Okay, so it cannot be that we think of certain technology where the performance is great, but we need a very high annealing temperature or something. Okay, so it has to be a low temperature compatible, and it has to be easy and roll-to-roll printable. That means what? Again, when you think of roll-to-roll printing, that means it has to be a fast fabrication. So you cannot have one intermediate process which takes even minutes. Okay, so the whole thing would be like, let's say you print some ink and cure it with laser, and the whole process is at least that fast that you can do roll-to-roll printing and large volume production. It should not be that it has an intermediate step where I need a curing time of 5 minutes. Okay, that's not possible. And now it's a little bit old view graph, but this is again a view graph taken from ID Tech X, one of the older market survey of theirs. I mean, this ID Tech X, I mean, some of my view graphs are taken from their market survey. This is a Texas-based printed electronics market survey company, and here it shows some market volume of certain printed electronic technology. But as I said, these are few years old. This is not very up to date. But what we can still take away from this view graph, that certain technologies I already mentioned are already very mature. It's over $1 billion. Okay, so like OLED display, I already mentioned conductive inks and different type of sensors. Whereas logic and memory on the left hand side, logic and memory is something which is very underdeveloped, and I can tell you why. Before I go there, let's start with some 2-terminal device, printed 2-terminal device. So let's start with just a PN junction diode. Okay, so this PN junction diode was printed and performance was it has a high rectification, and it could go even beyond gigahertz frequency level, and it was printed using antimony doped silicon as N-type, and Nb2 silicon as the p-type particles. So niobium, Nb2 silicon as the p-type, and antimony doped silicon as the N-type, and then we can have rectification, and also which went up to beyond gigahertz frequency. As I told you, that the printed OLED has the maximum success. So the John Rogers group already shown in 2009 that printing of LEDs, and this is on the right hand side, printed RGB. This is a quantum dot display, by the way. So it is by Nature Photonics in 2011. So printed OLEDs are really market ready. We can print OLED displays front end, okay, not the back end, not the electronics part, but the front end we can really print. And this is a recent development, those were a little bit earlier. This is a very recent in 2021 development of a where TCL and Juhua printing, they showcased inkjet printed 31-inch FHD rollable hybrid quantum dot and OLED TV. So this picture actually is not a very high high resolution, but this is a TV which is inside a case, and the screen can come up and go down, so the display is even rollable. Okay, so it can appear like a small piece of furniture, but you can press a switch and can get a screen which is rolling out, and which has a HD means high definition, so it's a high definition display and made of quantum dot or OLED. Similarly, photovoltaics. There are also examples of different type of photovoltaics. Amorphous or crystalline silicon, cadmium telluride, gallium arsenide, then SiC, then dye sensitized, and very recently, there are perovskites. Okay, so among these, I can just show you one example where SiC type of solar cell or photovoltaics was fully printed. So photovoltaics, OLEDs, what we see, okay, it's a diode-based device. It's the success is much higher. When we go to 3-terminal, which is the case of transistor, the complexity is much larger, and the success is low. Okay, so now we also give you some try to give you some overview of that thing. Before we go there, I just thought that maybe the entire audience is not may not be these were probably introduced to you even at 10+2 or a little bit, but may not be that you really remember what is a triode or what is a transistor. Okay, so just I wanted to give you a cross-section view of a MOSFET. So in the left and right hand side, we see a so-called top gate, bottom gate, top gate, and top gate and bottom
Hello, sir. Subho, sir. Am I audible? You're not audible, sir. Please check your mic. Yeah, since 2 minutes you're not available. I mean, your voice is not audible. Please check your mic. Please mute yourself and again unmute yourself. Hello, sir. Are you there, sir? Are you able to hear me? Participants, please wait for a while. Till then, we will be sorting out the technical problem which the speaker is facing. Thank you for your patience.
Now can you hear me? Yeah. Okay, yeah. So something happened in between. I don't know.
Okay, sir.
So
Now we
I
are
don't
able to hear
know
you.
until which slide you could hear me. So let me. Can you hear me now?
Ah, yes, sir. Go back, sir.
Again.
Yeah, go back.
Can you hear me now?
Yes, sir. Crystal clear.
Hello, can you hear me?
Yes, sir. We can hear you. Start with the previous slide, sir.
So can you hear me now?
Yes, sir. We can hear you.
Okay. So can someone respond that until which slide? I mean, I don't know. I mean, when I lost you. So until which
Yeah,
slide
go
you
back
could
to
hear
a
me?
previous slide, sir.
When I introduced
Previous slide, sir.
MOSFET, you could hear me.
Yes, sir. Keep going to the previous slide, sir. We'll tell you.
Hello? Dr. Pradeep, can you unmute yourself and help in this regard that
Sir,
when this connection was lost, I'm not sure.
Yeah, I have unmuted myself. I'm speaking, sir. You're not able to hear me? Hello?
Anyway, so I think...
Sir, you are audible, sir.
Yeah, you are audible, sir.
Now can
You
you hear
both
me,
are audible,
Pradeep?
sir.
Yes, sir. You can. You are audible. Please check the chat box also, sir.
Hello? Hello?
Hello.
So you can hear me now?
Absolutely, sir. We are all able to hear you, but do not know why you are not able to hear us. We are able to hear you. We can see the slide. Everything is fine. But if you are not able to hear us, then that's the only thing that you need to be.
Okay, but I just wanted to ask that until which slide you could hear?
Yeah, for that you need to go back, keep going back, and we'll say, please stop from there. You can stop.
So...
yes, sir. Yeah, no. Next one.
Here?
Yes. No. Previous. Yeah. I think you're there.
Okay, thank you. Okay. Yeah, for some reason, I think, I was in doubt in between that if you could hear me and that the problem started. Anyway, so no problem. We had a 5 minutes pause to digest something, right? So I was saying that, I think we are still on time. It's fine. I was saying that for this, general audience or mixed audience, I wanted to introduce the, Mosfet device as well. And there I just said that, this is a cross section of Mosfet, top gate and, bottom gate geometry. And here the current through the drive and source, drain and source electrode, which is called the drive current through the semiconducting channel, which is shown in green, is controlled by a additional voltage applied to the gate electrode, which would help accumulate charges at the channel insulator interface, and then those charges can be moved from one electrode to the other, one drive electrode to the other, by application of this other voltage, which is called VDS. So this is also a picture taken from the book of SM Shi, where different type of transistors are introduced. Very briefly, these are N-channel enhancement mode, N-channel depletion mode, P-channel enhancement and depletion mode. What are these? These are in very very briefly, I can say that these are the devices which are either where the predominant charge carrier is electron or holes, and then we call it N channel and P channel. And if there is already a channel, if the semiconductor is already conducting to start with, the doping density is high, and it is already a conducting channel or not, that will determine it is enhancement mode or a depletion mode, normally on or normally off device. Where it is a normally off device, therefore at zero gate there is no conductivity. You need to apply a positive gate for a N channel or a negative gate for a P channel in order to initiate the conductivity inside the semiconductor channel, right? So this positive or negative gate will have certain type of charge carrier. It will induce certain type of charge carrier inside the semiconductor. For example, if I go a slide back, if I apply a positive gate within this insulator, near the gate it will be polarized with negative charges. Near the channel it will be polarized with positive charges. So negative charge carriers or electrons will be accumulated, and then for an N channel with a positive gate I can induce new charge carriers, electrons, and can have the onset of conductivity. Okay, so which is called a VT, threshold voltage. Okay, so then we were talking about certain semiconductor technologies beyond silicon, which is considered in printable electronics. So one is a well-known organic semiconductors. Okay, so this has started way back in 1985 when conducting polymer was invented, and then from 1985 to in 2020, in last 35 years, we have gone to a large extent from a electron mobility of 10 to the power minus 5 centimeter square per volt second to around 1 or few centimeter square per volt second, which is shown now. Okay, but still organics also have certain advantage, obviously, like they are easy to print, easy solution processable, they are extremely flexible and bendable, low temperature processable, but they also do have some problems like low mobility. I mean, this carrier mobility, one or few, one or two, three. I mean, inorganics typically do have higher mobility values, not only in the range of 10 to the power 0. They have higher values, and there are reliability issues, environmental stability issues, lifetime issues, and so on. Okay. Now, question is that what are the alternatives? One alternative we have started to look for, from around 2005-ish. It is called oxide semiconductor or printed oxide electronics. Okay, so the point is oxides are a and silicon when we talk about the mechanical property. For example, silicon is covalent, which is extremely brittle. Okay, oxides are ionic. Okay, and then amorphous oxides are also there, which can take a little bit of organic material is typically can show band transport and very high very good electronic transport properties. Okay, whereas organics, most of the materials are that electronic transport is by hopping. Okay, and here very recently, I mean, these pictures is actually taken by me from a conference in South Korea. South Korea is very aggressive in oxide electronics and also in printed electronics. So these are two display. One is by Samsung and one is by LG. Okay, what is the Samsung display? You can see some human being in the background, right? So this is huge, gigantic display, and it's fully transparent. I think you can see something in the background as well. So it's a fully transparent display. Like I said, it will, if we switch off the display, it will be like a glass. Okay, I mean, a glass anywhere. Okay, it can be a window glass or wherever. But if you switch on the display, it's just a display. Okay, then that means that this is an example of transparent oxide electronics. Okay, so these oxides, what I'm talking about, these oxides are typically N-type electron conductor, the good ones. There are P-types as well, but the good ones are N-type electronic conductors, and the good ones are called high band gap semiconductor. They are typically called TOS, transparent oxide semiconductor. So this is a group which indium oxide, tin oxide, zinc oxide, they are very high band gap. Okay, so they are transparent in the visible spectrum. Okay, so they can really be used to make transparent display. The other example is LG stall, where it's a bendable display. I mean, I don't know if you see it. It's a curved display. The display is very much curved, and the picture will be also curved. Okay, so you can. I mean, this is just a demonstrator, and it has a ugly curvature. But on the other hand, nowadays there are new displays and televisions are coming where it will have you will face a concave display, and if it is a large enough in size and you watch a football match, then you will really enjoy. You feel like you are in the stadium. Okay, so that is the kind of feeling it will give if it has a concave. You are facing a concave side of the display, and all these are made by so-called amorphous oxide, indium gallium zinc oxide technology. So when you go for UHV, but these are UHV grown, okay, these are sputtered and so on. So when you go for UHV, the oxides have already proved that they can be commercially successful. Now we need to see that in case of printed electronics, if this success can be replicated. Okay, but there are challenges with process temperature, problems with downscaling, mechanical reliability, and variability, and other reliability issues. All these things are there. Now, before we go further, this slide also gives us some, two information. Why oxide is better than silicon? Okay, so the left-hand side, the column shows silicon, and the right-hand side is oxide. Okay, so what we need to see here, as I said, silicon is very bad for flexible application because it's a covalent crystal, and covalent crystal has a very specific, directionality. There are bond angles which has 109 degree, and they are 109 degree. You cannot change it. And what happens when we go? For that, when you go from polycrystalline silicon to amorphous, then we decrease the benchmark performance parameter. We will talk about this performance parameter every now and then. From now on, it's called mobility, carrier mobility. This benchmark performance parameter decreases from 200 to 300 centimeter square per volt second in case of polycrystalline silicon to only 0.5. Okay, so this is what happens if you have a covalent semiconductor. But oxides are ionic, and the band transport in case of an N-type oxide, for example, indium oxide, they come from NS orbital. And as you know, these are S orbitals, so they are spherical, and in case of indium oxide, they are 5s, so they are really big also. Then what happens? Either they are crystalline, they are very nicely arranged, like it is shown here, or they are amorphous, very randomly arranged. Doesn't matter, because spherical orbital cannot have directionality. Whichever way you place it, it will give you band transport. Then what happens? That in case of silicon, it was 200 to 300 centimeter square per volt second for polycrystalline. Single crystal is 1400. Okay, for polycrystalline, 200 to 300 centimeter square per volt second. For amorphous, it's 0.5. But for oxide, indium oxide was 100 centimeter square per volt second, or 200. For amorphous, IGZO, what I written here, IGZO, indium gallium zinc oxide, is also 50. It doesn't destroy that badly, but there are advantages if you go for amorphous. One advantage is no spatial directionality. What does this mean? That no spatial inhomogeneity. What does this mean? If you have and if you have a crystalline material, there are imperfections. Okay, there are grain boundaries and other type of imperfections, and there can be different size of crystals and so on. So the performance will vary. Okay, but for amorphous, it's featureless. Okay, and it can be very homogeneous, spatially homogeneous for a large area, like a big display. Okay. Here I give you another this view graph just to promote this idea of this amorphous oxide semiconductor a bit further. This is between indium oxide, zinc oxide, and gallium oxide. We can see that only pure indium oxide and zinc oxide is crystalline, but everywhere else these are amorphous, and this is a mobility contour. So you can see the pure indium oxide is highest mobility, and of course, gallium oxide is bad, because of course, if it is crystalline gallium oxide, beta gallium oxide, it can be very high, but that to get there you need to go to very high temperature, which you cannot do on inexpensive substrates, right? So you are talking about amorphous gallium oxide, mobility is very low, but you can find the contour here, okay, where indium oxide is higher amount, some amount of zinc and some amount of gallium, it is amorphous according to this, but the mobility is also not that bad, and that is what we use. Now, some other technology, semiconductor technology, which is also used in this case, or also people have tried. This is a case of CNT network transistor. So people have printed semiconducting CNTs. Okay, so hello.
Subho sir, আমি দীপঙ্কর বলছি এমটক থেকে।
So here again, here again, some success has been there with this printed CNT network transistors, but there are also issues such as toxicity, because single wall carbon nanotubes, they can be toxic because they have a very high aspect ratio, and once you get them inside your body, let's say if you breathe in, they will stay there forever. If your body doesn't know how to get rid of them, because they have a very high aspect ratio. It's like a thorn which goes inside your body fully. It's very difficult to get out. Okay, or if you eat a piece of hair, that's why we are so afraid of eating hair. Once it goes to your stomach, it will never come out. Okay, so anything which a very high aspect ratio is bad for your health, and this is additionally bad because they can be they have some catalytic property as well. So large scale use of CNTs is a problem due to the toxicity aspect. On the other hand, the cost is also a problem because the chirality sorted carbon nanotubes you need here. You need semiconducting carbon nanotubes which are chirality sorted, and they are very expensive. Another is solution process network TMD, transition metal dichalcogenides. These are next to graphene. These are new 2D semiconductors, but this is also at a very nascent level. Okay, so these are just evolving. People don't have very good, transistor performance yet. Now the next question was, this is all about transistor. Okay, what about dielectric? Because in printed electronics we say that either you print all or you print none. Okay, so what about dielectric? Typically people have reported silicon oxide or sputtered L2O3 or various high K dielectric or organic dielectric, etc. But many of them are not printable, and in printed electronics we should print every component, otherwise there is no advantage in terms of volume production or cost. So there is one idea is, if we can use electrolyte as a gate insulator. What is an electrolytic insulator? This is in the left hand side. This is a picture from Bell Labs. It's a point contact transistor, the first transistor made by human ever, in 1947. But on the other hand, the first transistor, only few know that before going to germanium oxide, people have tried water as a dielectric. So the first transistor ever made by man was also a electrolytic transistor. Here the idea is to use the Helmholtz double layer of when we have a electrode material inside a electrochemical environment, there is a Helmholtz double layer or charge double layer forms at the interface. Okay, and that is very much analogous to a dielectric dielectric gating. Okay, that is very much analogous to a dielectric gating. We can also have a electrolyte use as an electronic insulator. Again, here we want to mean is that we want an electrostatic field effect and not electrochemical doping. We don't want chemistry. We want a pure field effect. And this is a view graph which exactly shows, we call it an onion graph, okay? So it exactly shows, this is again a cyclovoltammetry, which exactly shows that at the center, you know, it is pure electrolytic field effect, is a capacitor behavior. In a when you do a cyclovoltammetry, if you see a constant current, that means it's a pure RC circuit. That means it's just a capacitive, you know, just a like a capacitor, like a dielectric behavior. But if you see this kind of, you know, redox peaks, oxidation and reduction peaks, then that means the chemistry is involved. So this is what just the purpose of showing this is that you need to choose the right electrochemical window in order to have a electrolytic field effect, electrostatic field effect. Okay. Another good example, you know, was by a group by Frisbee, that beyond the applications we have talked until now, there is a large application domain also in bioelectronics. Okay, and for that, this is a good example where we have a so-called cut and stick rubbery electrolyte. It's an ion gel based electrolyte which you can just simply make a piece and paste it on the device, and this works like a transistor. So these are P and N type transistor performance has been shown with this kind of cut and stick rubbery electrolyte. Question is, what can be the speed of this electrolyte getting? This we have shown by calculating the cutoff frequency, that this electrolyte getting can even on the size of the channel length and depending on the thickness of this electrolytic insulator, because ultimately it is a RC circuit. Okay, so this is the derivation from a impedance measurement. Considering a certain equivalent circuit, we made this derivation, and there we get this maximum frequency of 10 megahertz even can be achieved with optimizing everything. This is a nanowatt transistor, single nanowatt transistor, where we have shown that in fact you can see the tau 1 and tau 2 value, the relaxation time of the order of microseconds. Again, from the Frisbee group, they have shown a CNT carbon nanotube based circuit, which is a benchmark circuit. Is called ring oscillator, where the switching frequency was 22 kilohertz. So up to that level they have shown, and that is the present world record. But there are some other technologies where we will be able to show that even hundreds of kilohertz might be possible. Okay.
Hello, sir.
So now,
sorry to interrupt, sir. Can we conclude the session in about 2 minutes, because we have another session coming up, and we also have a Q&A session.
Yeah, so right now. Try to summarize in 2-3 minutes. I am very into it.
Okay.
Anyway,
sir. Thank you, sir.
Okay. So this is some other aspects of the oxide electronics, which I wanted to show you some examples of other challenges which try to address. So due to the time constraint, we lost some time, so I try to be a little quick. Okay, so process temperature, there were some examples by a Northwestern University group where they have done something called combustion synthesis. Okay, so they added a fuel inside the electronic ink, which reduced the process temperature. What we did, we did something like a chemical curing. So this is a nanoparticle ink where there is a certain chemical inside which will destabilize the ink, the dispersion, once the concentration of that chemical reaches a certain critical value. Then what happens? So when we print the ink, during the drying process, that critical value is hit, and then the dispersion gets destabilized, the ligands are gone, and we get a very high quality nanoparticulate film. So this is without the additive. The left hand view graph, SEM image, right hand view graph is with the additive, and we can right away see a very large change in conductivity. Also with additive, the ligands are gone, high conducting. Without additive, the ligands are there, it doesn't conduct. Okay. And this is also approved. The experience data, it shows the chemical curing is working, and we have demonstrated fully room temperature printed transistors, P and N type, and some inverters and so on. The last thing of my talk is this: that one problem of the printed technology is device miniaturization. For silicon technology, we talk about 14, 11, 7 or 8 nanometer node, whereas the printing technology is at the range of tens of micrometers. Okay, so this is a very big problem because the channel length determines the speed and it's also squared. Okay, so in order to solve that, there was one approach from a Cambridge group who did so-called self-aligned printing, and we have done also something called the vertical transistor. Since we have a bad resolution in XY, we wanted to use the Z dimension, so we made a device like this, where the source and drain electrodes are not placed on the same substrate, but they are vertically aligned, and then they have a nanoporous channel in between, okay, and that got infiltrated by the electrolyte, and we have transistors with extremely high, close to a mega ampere per centimeter square current density. Okay, so this is these are some examples I wanted to show you in relation to the challenges in printed logic electronics. As I said, when it's two-dimensional device, some diodes, OLEDs, or photovoltaics, these are near to commercial success or already commercially been demonstrated in a large scale. But when it comes to three-terminal device like transistor, then there are the challenges are more. Different semiconductor and insulator technologies people are trying, organic, oxide, and CNTs or 2D semiconductors. And in terms of dielectric, it can be high K dielectric, and all organic dielectrics, and also this electrolytic field effect. Okay, so this is, I end my talk here. I don't have a summary slide because it is not easy to summarize, because I talked about two different domain. One is different type of novel emerging electronic device where you apply a stimulus and get a change in material property, and then I focused into flexible and printed electronics, where I have shown you some of the examples of what is going on in the world, and some results also from our own research group. Okay, and this is my group member, and these are some funding sources. Okay, and I think I overran the time because of some interruption and so on, but maybe there would be time for a few questions.
Thank you, sir. I thank you for sharing a key insight about electronic materials fundamentals and processes, and also on flexible and printed electronics. The main reason why we chose electronic materials as a session in this FDP is electronics plays a very significant role in our day-to-day lives, such as we use mobile phones, electronic gadgets, and also TVs and other displays. So coming to the participants, if you have any questions, you can ask sir orally, or already there are 3 questions pending in the chat box. Sir, if you can look at the chat box, and if you can answer, it would help the participants, sir.
Okay. I think my system has turned a little slow. Okay. It would be nice if you can read out the questions.
Yes, sir. Yes, sir. The first question is, sir, what is the level of troubleshooting difficulty or possibility in the printed electronic boards?
Okay, so the point is, I said that printed electronics has different semiconductor technologies, organic and oxides. They have their own challenges. Okay, but other than that, the one common thing, I mean, couple of challenges which are common for printed electronics. One is, or let's say 3. One is one is miniaturization. I just touched upon at the end. Second is variability. because it's not like lithography, right? If you print, you can expect a little bit deviation from one device to other, and there will be variability. And if you come from solution, the third problem is reliability or lifetime, how long the device will survive. So we are trying to address these challenges and trying to solve them. As I said, two-terminal device, OLEDs or photovoltaic is easy. Three-terminal device, transistors are not easy because it's much more complex. But I think we have made a lot of progress in the last 2 decades, and we are hopeful that there will be something in the market in this decade already.
Okay, sir. So next question is, how durable is printed electronic boards compared to regular PCBs?
No, the point is you should never compare printed electronics with silicon technology. Silicon technology had huge funding, huge research attempt, research force in terms of simulation and also experimental, and it's a most dominating market of last 4 decades, okay? And it has been developed so much that, as you know, that we are talking about 7, 8 nanometer nodes. So it's up to the last nanometer or maybe even last angstrom, everything optimized. So you cannot compare, don't even, I'm not really probably answering the question, but my point is not, one should not compare the silicon PCB with printed electronic because the application is not the same. Here the application is most likely, let's say, if you take wearable electronics, I want to put an interactive tag on a consumer goods product where the lifetime of that electronic should be a few months or even less. I don't need a microprocessor which needs to survive for years. There are many applications where even surviving the technology for months would be enough. But that is what I just mentioned. Environmental stability and lifetime and reliability. That is the main thing where we are working on. But let's not compare silicon and printed technology.
Okay, sir. So the next question is, sir, in electronic printer, do you use any software to print required circuit?
Yes, so there are, as I said, there are 2 types of printing. One is replication type, where there is a master roll typically, okay, and one is jetting type. Under jetting type, there are inkjet, aerosol jet, and other jetting techniques, and these are digital printing techniques. So every morning, my student can decide what to print. So you can even print, BMP image out of electronic ink. You can print whatever you want. It's like an inkjet printer. It's like your office desktop printer, but it's an electronic functional printer. So my printer has higher resolution and it can handle those electronic inks, but it is like an office printer. You can print what you want. It's a digital printer.
Okay, sir. I hope Prema Kumari sir has answered all your questions. Is there any other question from participants? You can speak it orally if you want. Yes? Anyone?
Yeah, please feel free. Don't be shy.
Hello, sir.
Yeah, hello?
Audible, sir?
Yeah, Dhananjay.
Yes,
sir, when you discuss about stimulus in the second or third slide, we are not discussing about stress and strain in the electronics methods, or you can say mechanical, you can say that. So this stimulus are affecting.
One second, Dhananjay, can you, you need to repeat. I did not understand.
Okay. So when you discuss about different stimulus in functional material or structural materials, you will not highlight about stress and strain. Is it a stimulus that affecting?
This is an excellent question. This is also a good question. Applied stress can be applied and removed. And for example, piezoelectrics, right? If you apply a stress, then you can generate some potential, right? So as I said, I'm sorry that I did not include stress and strain, but I think I have mentioned there that this table is just a beginning, okay? I can't include everything. There is many things beyond this. right? So this table should be just you can take it just your starting of your thought process. And I think this table is still incomplete. This table is not complete. You can have your own invention. Think of a new stimulus and a property combination, okay? And then you have a device, okay? So this table is ever growing. And of course, I did not show the entire table. There are many more examples. You are right. Stress can be a stimulus and you can change the property. Correct.
Next is when you discuss about DMS, then the diagram can you show, sir? There is you discuss about there is two materials. You can magnesium have that nanoparticle is look like a half sphere. So can you explain that by DMS? Dilute magnetic semiconductor.
Yeah, understood. But there are a lot of slides, so I'm trying to go back.
Yes.
Fine.
Yeah, my question is that MNG particle is half sphere, even same also, even your schematic diagram also. So that particle, how it becomes half sphere like this? So
no, this is just I have to go back to this paper to answer your question specifically. So it's good that these quantum dots, why they look like specifically this. I mean, this would be related to some sort of a growth technique. I don't know now how they have grown it, but you can see in the cross section TEM is just not the schematic. In the cross section TEM also it is looking very similar. But I'm sorry, I cannot answer. I have to check that paper.
Last question. When you discuss our biomaterials, can you printed the biomaterials on this printed electronics?
Yes. But that would be an entirely different talk. I have to talk 2 more hours. If I talk about printed bioelectronics, I didn't even dare to touch, because this is a huge arena. So many, it can be biosensor, it can be different, in vivo, in vitro application of, I mean, this John Rogers group, they are working in this domain since last 20 years, right, or even more. So this is a huge thing, right? It's better, I mean, I thought it's better not to touch that. If you talk about bioelectronics, what we do typically, that in the transistor geometry, somewhere we put a bioactive layer. Okay, so that can be at that gate interface can be decorated, or one of the dielectrode interface can be decorated, or the semiconductor surface can be decorated. So somewhere you will put smartly a bioactive layer for certain purpose. Even for SARS-CoV-2, we have a transistor based, I mean, it didn't scale up or it's not in practical use, but there is an example of a transistor based, detection or of SARS-CoV-2, virus.
Last question, as I do my research, related to array transistor.
Related to?
Array transistor means lot of transistor should be arranged. Array
transistor. Okay, yes.
Is it possible on this printed electron?
No, in printing we do array printing. We never print a single transistor because you can't print like that. So that is the thing, when we want to print a circuit, I mean, why should I print one transistor? I mean, the printers, as I said, it's like, you can feed in different sort of files in those printers, different sort of file format. So what we do, you can also design it externally and feed in, or you can locally design it in that PC itself, within the software itself. And typically in our lab, we never print a single transistor. That's nobody does. Okay, so you will print array anyway, and this array can be as big as you can think of.